Labas ritas. Yeah, my name's Kieran Walker. I'm an associate at Waugh Thistleton Architects. I've worked there for about 8 years. This is us in one of our Christmas card photographs. We do these funny things every year. We're a studio of about 30 people, founded by directors Andrew Waugh and Anthony Thistleton about 21 years ago, based in central London, but we work across Europe, including projects in France, Sweden, and predominantly the UK. We work across lots of different sectors, so predominantly residential sector, apartments, private houses, and increasingly we're also doing a lot of commercial office projects, again, particularly in London at the moment. We also do other things like Jewish cemeteries, which is a bit different, and we also kind of do master planning projects and things like that, so all sorts of different scale projects. And that kind of gives you an example. So we've done CLT projects on private houses all the way through student living and larger apartment schemes. So a real kind of diverse mix of projects within our portfolio. We've worked for lots of different clients, so Vastant, who I know are a large company across Europe, we've done quite a bit of work for. Berkeley Homes and the Office Group, two of the largest kind of development companies for residential and commercial in the UK. So we work with kind of lots of different people, and we really enjoy kind of collaborating with our clients. We always think that design is a process, and that working with the clients is the best way to get the projects that we want and they want. We're also very much involved with academic research and work closely with lots of universities. So we have a good relationship, particularly with Cambridge University and Michael Ramage there, who is heading up their materials department. We do quite a bit of teaching. So my boss, Andrew, particularly, he lectures across the world at places like Yale, lectures in Switzerland, in Scandinavia, and he's not here today, you've got me, but it's all about getting the message of CLT out there to everybody. Award-winning practice, so a lot of the work we've done, although it's kind of CLT and timber orientated, design is at the heart of everything we do. So CLT to us is a design tool that we use to create our buildings, and a lot of those have been recognised with awards, which has been fantastic. As an architecture practice, we offer kind of standard architectural services, so we take projects all the way through from concept to completion. I think when you're working with prefabricated products like cross-laminated timber, it's really important that you design from first principles with CLT in mind. The greatest benefit to a project when you're using these sorts of technologies is to integrate them at the very early stage. So we always feel that we can give the best value when we're involved at the start of a project, and then see that all the way through. So as designers, we're very interested in how things are connected and how they go together, and we think the best projects come from that understanding. That's not to say that we don't just kind of work at early stage stuff, so we can do kind of concept design and what we call planning sorts of designs, and often we will stay kind of client side during procurement to ensure that the building is delivered in line with its design intent. Increasingly what's happened over the last kind of 2 to 3 years is that our expertise in timber has been attractive to different clients. And so we've been approached by various people to take an existing building or an existing planning consented scheme and then complete the technical design using CLT or engineered wood products. So some of these projects that are on the slides here were traditional schemes using concrete that we then took CLT and integrated a CLT structure. The project in the middle there is a project for Vitso, which was a kind of conventional looking factory, and that was developed in the same way that you might develop a furniture product. So it was about using all the available timber products in the market to create this kind of amazing, precise kit of parts that created a factory. So why do we use CLT as a practice? Fundamentally, for Waugh Thistleton, it's about trying to limit our impact on the planet and try to make a positive contribution to reducing carbon dioxide emissions. So the reason we use timber as our main kind of product within our buildings is very much that it promotes decarbonisation and kind of the forestry economy. So by planting more trees, we're absorbing more CO2, and if we can create a market for that activity to occur, then we can promote that reduction in carbon dioxide emissions. Why is that important? Well, if we look at concrete and steel, they're huge contributors to our climate problem. The production of cement and concrete in particular is very energy intensive. There's obviously a lot of steel that goes into our concrete buildings to reinforce them, and these products take a lot of energy to make. And if you consider concrete and where the sand comes from and things like that, then we are having a large impact on our planet. So the use of timber for us is to try and move away from these traditional construction materials that were kind of the 20th century materials, and using timber, try and find an architecture for the 21st century. Also, another good reason to use kind of timber products is that the buildings that we're creating these days are very airtight, very well performing. The building regulations and standards necessitate that the energy we're using, or the energy that these buildings use once they're in operation, is relatively low. And what's happening now is that because that's becoming so low, the embodied carbon of the buildings that we're creating has a much greater impact on the overall kind of carbon profile. So we're really keen to have, to put the discussion and the argument out there into the industry that embodied carbon is just as important or more important than operational carbon. There's obviously room for both, and we have to think of that in a joined up way. But at the moment, a lot of statutory legislation, lots of the kind of measures by which we judge sustainability is weighted to operational carbon rather than embodied carbon. And we think that should change, and we think that timber can obviously help that. And yeah, so CLT, just by its nature, is sequestering that carbon within the product, and then that carbon, once it's in a building, is locked away. It's important to understand that the process of creating engineered wood products is actually a very low waste process. So once those trees are forested, the timber from those trees can be manufactured into various different products. With CLT, as we've just heard, it's about small pieces of timber laid perpendicularly to each other to create strong panels. During that process, any waste from the cutting and the manufacture of those products gets put back into the manufacturing cycle. So if you've ever been to one of these plants in Austria, you'll see that the waste wood contributes to the energy to drive the machinery within these factories. So it's a real holistic process from forestry all the way through to manufacture. And if we consider that manufacture as one part of this kind of circular economy, then we can lock away that carbon within the buildings that we're creating. And that's the kind of process we're trying to encourage. And so the Murray Grove project, which again we've seen briefly just a minute ago, was the kind of first at-scale realization of our ambition to create a low-carbon building. This, for example, was a 9-story residential building. I think there were 47 apartments in there, and this was completed in 2008. And this is kind of regarded as the first timber tower, if you like, and for us, the first proof of concept that CLT can be used to create large-scale buildings that will sit within our urban environment. Our experience from that really kind of shaped the practice and has shaped the practice over this last 10 years. So we've really become specialists in a sustainable architecture. We've become specialists in delivering CLT buildings and using prefabricated products to develop our schemes. We don't just use kind of CLT in panel format, but more and more we're exploring what we can do with CLT by using it in kind of hybrid arrangements, so using panels in combination with steels and glue lams to create frame and panel buildings which give us larger spans. So if you look at that slide on the left, that's a kind of typical commercial office building for us where we're using panels in conjunction with kind of column and beam elements. We've also worked recently with Legal & General and Swan Housing. Legal & General in the UK are a particularly large company. who are finance experts, but are getting into this modular housing market. The context in the UK at the moment is that we have a huge housing crisis. There just aren't enough homes for the nationals there. And modular volumetric ways of constructing is seen as one way of addressing this housing crisis that we have. So we've been working with those companies to develop CLT-based volumetric housing products. And that's certainly a growing market over there, we think. And yeah, just to say that CLT is very versatile. So, we've got a simple panel down there on the bottom. But we can use that in many ways, whether it's creating full-scale prefabricated rooms or pods, if you like, that can be transported to site with all the finishes and everything else applied. That's one option. The other option is a kind of flat pack option where panels like that will come to site on the back of a lorry and then be bolted and fixed into place to suit the very specific requirements of the site. So subject to what type of building you're doing and what sort of site you've got, the choice of which way to approach that building site, there's flexibility there in the way we can use those products. So as an example of a flat pack, and I'll talk more about this in a second, this was our Dalston Lane scheme, which, as we'll see, there's a good reason why this was flat pack, but the whole scheme was developed with just simple panels like that screwed together on site. And that's it when it was completed. This again is the Vitso factory, so we can see that there are CLT panels forming the kind of underside of the roof and some of the walls at the far end. These are used in conjunction with Baubucker LVL beams and columns, as well as steel. So this is what we would call a kind of hybrid CLT scheme. But everything here was designed to within plus or minus 2 millimeter tolerances. Vitso, being a furniture manufacturer, were very, very keen that the building was like a piece of furniture. And this is where engineered wood really played to its strengths, if you like. Because we were able to get really tight manufacturing tolerances, even between all these different products. There's just another view of it there. This scheme here was a student scheme in Brighton, and this scheme was for 57 studio apartments, student project. The scheme had to be completed within 10 months, and we used lots of different modern methods of construction to complete this, or lots of different prefabricated technologies. So we had closed timber panels, we had structural sit panels, we also had CLT floor slabs, prefabricated bathroom pods, and prefabricated brick cladding. So it was a real juxtaposition of modern methods of construction and a real showcase for what you can do using prefabricated products, including CLT, but not limited just to CLT. So again, lots of low waste products from low waste processes. And that's a complete scheme again there. And then as I touched on with the volumetric, we're doing more and more work in the volumetric modular sector, particularly residential, on the basis that we've got this housing crisis. And our first kind of multi-story CLT modular scheme is coming forward. That's at Watts Grove, which is a site in central London. And that will be a multi-story scheme with lots of different CLT modular types. It's the first kind of project for our client using this technology. But it gives them the flexibility to create all these modules in the factory and then deliver them to site and construct very, very quickly. So the benefits of this approach is that once you get on site, the build program is vastly shortened. All that work is completed to create the modules in the factory. So you've got your bathrooms, your kitchens, your finishes all completed in the factory. So it's on site at the moment, but this is what it'll look like when it's completed, all being well. And off the back of that process, we took our kind of education from that process to create a modular design guide so that other architects and engineers going forward could better understand how to design with the CLT modular system. So it's a really important project for the client and really important project for our office, and really demonstrates what you can do with CLT in a modular volumetric context. And if you really want to push it, this was a project we completed this year for the London Design Festival. So this project was called Multiply. It was a series of tulip wood CLT panels that were bolted together to create smaller CLT modules that were then transported to site. So this is kind of a combination of flat pack and volumetric modular, and really demonstrates that timber can be used in so many different ways to configure different types of architecture. So there's no one size fits all, and even though we always want to try and use timber, there's lots of kind of versatility with that when you do so. And so far now we've completed over 20 CLT buildings, and we've got more on site at the moment, so we've become kind of real specialists in this area. Just to look at a bit more detail at the Dalston Lane project. So the Dalston Lane project was a project I worked on for 3.5 years as a project architect. It is a scheme for 121 apartments and 3,500 square meters of commercial office space. It is the tallest CLT building in the UK and one of the tallest in the world. It's 10 stories at its highest. We've got about 8,500 square meters worth of residential floor area. The building incorporates 7 separate cores which serve the residential apartments. And then the commercial space kind of links those together, as we'll see in a second. The building's located on a former industrial site within East London. And one of the main constraints of that is that the scheme is surrounded on 2 sides by roads, and at the rear of the site we've got existing buildings. And those buildings vary in scale, and the context varies in scale between kind of domestic and urban scale. So the arrangement of the building is very specific to its site in terms of its plan layout and its massing. So the massing was developed to obviously respond to its surrounding area and to maximize daylight into the apartments. So the building's kind of characterized by having several different volumes at different heights. And that's just a view from above, so you can see to the south there's some existing buildings, and also to the west there are some existing buildings and those roads around the side. The other main constraint for this project, and the key constraint that led it to become a CLT project, is that the scheme is located directly above the future site of Crossrail 2. So Crossrail 2 is a kind of high-speed rail link that's going to be created between North and South London. And because the location of that is mapped out, there were some certain rules as to what you can and can't do above that route. So at Dalston Lane, what this meant was, due to that railway line, we weren't allowed to build a building using concrete piles, because the concrete piles would have interfered with the train line below. So this necessitated that whatever we did would have to use a kind of thick raft concrete slab foundation in order to distribute the load away from that future rail line. Now in concrete, that is obviously doable, but you would end up with a shorter building simply because concrete is a much heavier material. So the reason we kind of went with CLT on this was that CLT was the only way this site became viable and financially affordable for the client, because we were able to offer a greater density and a greater height, which made this a much more cost-effective project for the client. So in understanding that we would need to kind of deliver a lightweight building, we, as a design for us, or when we start out doing CLT buildings, we consider what the constraints of a typical manufactured panel are. We look at the different ways in which you can apply CLT, so we have to decide whether it's suitable for load bearing or whether we're going to need larger spans that might necessitate a hybrid solution. And at Dalston, with the majority of the floor plate being taken up by residential apartments, we knew that we were going to have to do a kind of load-bearing solution. So what you have there is a typical floor plan. What I hope you can see, it's a bit small, apologies, but what I hope you can see is that the apartments and the CLT are arranged in a kind of honeycomb structure. So we've got very short spans between structural walls. Each apartment has CLT party walls, so large CLT walls between each separate kind of apartment. And then within each individual apartment, we also have some load-bearing CLT walls. So this helps us to shorten the spans and allows us to do a load-bearing solution. The stair cores, the lift shafts, the stairs, they're all also solid CLT panels. And where we have the office link space to the south, again, we have CLT panels, but these are much deeper to get over the larger spans. So if we see in section there, at basement and ground level, what we have is kind of the concrete basement and raft foundation, above which we have a traditional kind of concrete frame, which then terminates in a first floor transfer deck. So at first floor, we've got a big, thick, 500 millimeter thick concrete slab onto which all our CLT is constructed. So we have a mix of heights across the building. That kind of gives you a sense of the variation in the massing. So at its tallest in the middle section there, that's our 10-story section. So that's about 34, 35 meters above ground level. And we can also see that the CLT, the cellular nature, both in plan and in section. Another thing we should point out is that the CLT at the lower levels is a lot thicker than the CLT at the upper levels. So as you go up the building, we're increasing the available net area, or sellable area, as the client would call it, which means the apartments get bigger as you get nearer the top of the building. So we're increasing the floor space by reducing the timber as we go up. And that just gives you a better sense of it in 3D there. So yeah, just a quick snapshot into one of the flats. So you can see we've got timber panels that are fixed down using just steel brackets. So it's a very, very simple approach. Those panels come to site, craned into position, and then screw fixed down. It's very quick, very quiet. And all the locations for these brackets, all the holes, all the openings, these are all designed at the beginning and coordinated in CAD. So it just makes it very simple on site. There's no building work, effectively. You can just bolt it all together like Meccano. Apologies, that's a slightly small one again, but with Dalston being a particularly tall building, there were some difficult fire regulations to get round. So in the UK, if a building is over 18 meters in height, we have to design it for 90 minutes fire resistance, which is what we have at Dalston. And then the stair cores in Dalston will have to provide 120 minutes fire resistance to allow for escape. So this has obviously been one of the largest timber buildings in the world, a particular focus of the design work. So we work closely with the engineers Ramboll to develop a strategy. And that strategy involved thickening the CLT to allow for that CLT to char in the event of fire. So what you will typically find in most kind of multi-story CLT buildings is that the CLT is designed to allow some degree of charring during a fire, and that time scale is taken into account when you come up with the overall kind of fire resistance. So at Dalston, the outer layers are designed to burn during a fire without compromising the structure. And then the CLT is also supplemented with plasterboard to increase that fire resistance to the 90 minutes and the 120 minutes that's required. As well as the fire considerations, we also had some typical kind of performance requirements. So at the time, we were aiming for BREEAM Excellent Standard and what's called Code for Sustainable Homes Level 4. Interestingly, both those standards, although they prioritize sustainability, it's mainly focused on kind of operational in-use energy use, and it relates more to how the building relates to its kind of social context. So, does it have bikes? Does it generate its own renewable energy? That sort of thing. So even though there were quite stringent sustainability criteria for us to respond to, none of those were, the CLT didn't contribute to meeting those targets by virtue of the carbon it was sequestering. So even though we're using a sustainable product and that product contains carbon, these sustainability standards in the UK don't give you any points for that, which I've never really understood, but that's how it works. We also, so the building fabric, we have quite high performing building fabric in terms of its U values, and the air tightness is also quite high, so we were aiming to achieve twice the amount you would usually require under the building regulations. Also, in terms of the acoustics, we had to bring about a 5 decibel increase in performance over the building regulations in order to get those BREEAM and Co for Sustainable Home standards. So how did this manifest itself? So just got some typical build-ups here. So a typical external CLT wall at Dalston includes a CLT panel of between 140 and 100 and 160 millimeters. And then that has a layer of, or 2 layers of plasterboard on the inside. And then we've got rigid insulation on the outside and a load-bearing brick cladding. In the lift shafts, we were able to keep the CLT exposed without lining it. What we did there was just thicken the CLT, and so all the fire resistance in the lift shaft comes from the CLT itself. In terms of party floors, we had very, very kind of thin floor build-ups overall. So if this scheme had been built in concrete, we would have had much thicker floor slabs and a taller building. So again, that was one of the reasons why it wouldn't have been viable to build this in concrete. Here, in order to get the 5 decibel improvement over the building regulations, we had a floor build-up that included a acoustic isolation layer and then a screed on top. That screed also contributes to giving extra mass to the building. So one of the challenges for the engineers during the design stage was that a building of this height, with it being lightweight, it would want to move in the wind. So we had to provide some kind of lateral resistance by increasing the weight of that building. And so the screed contributes to increasing that mass and helps make the building sit down on its site. Party wall there, again, we've got the 2 layers of plasterboard that improve the fire resistance, and then the air gap is insulated in between to provide an increase in the acoustic performance. But again, you get a very thin wall comparative to a blockwork or concrete frame type system. Roof, we've got kind of flat roofs here, or roofs with a very shallow fall on them. Again, nothing particularly different to what you would do in a kind of standard approach. I think it's important to understand that when you use CLT, you don't need to use different special products. You can use conventional building products that you would use on traditional schemes to supplement the CLT. So just because you use an innovative material doesn't mean you have to go and spend lots of money on new, innovative finishing products. Just a note on procurement. So this is one of the first times in the UK that the scheme was designed using the data from the 3 big suppliers, in this case Binder, KLH and Stora Enso. So our engineers designed it in a way that would allow for a competitive tender in order to improve the kind of value to the client. So it just meant at the design stage we had to allow for the thickest possible panels, and then post-tender we were able to identify efficiencies in line with the supplier's panels and work more closely with the supplier to try and reduce the amount of volume of timber where possible. In contrast to the Murray Grove project that I put on the screen earlier, this scheme uses a lot less timber way more efficiently, and that's just on the basis that 5-6 years later, since we did Murray Grove, we've learned a lot more. Engineers know a lot more about the product, and those safety factors now are better understood, so we're able to use timber more efficiently, which makes it more cost effective. One of the other constraints on the Dalston Lane scheme was movement. With it being a 10-story scheme, it's quite tall. So the action of the CLT and the loads transferring down the structure would mean that at the floor edges, where you have timber coming in horizontally, you get a force on that timber which would cause the building to creep and move. So from an early stage, the engineers decided that we would have to introduce grout pockets. So prefabricated holes in the edge of the floor panel that were infilled with a cementitious grout. What this allows us to do is transfer the wall loads straight through the floor to the wall below, which means the building is much more rigid and it avoids any movement or any eccentric movement. also to take into consideration, which this diagram on the right-hand side shows, is that the brickwork is supported from a masonry support angle that is set just below the floor slab. The reason for that is in CLT buildings, and particularly high-rise CLT buildings, the movement is always at that floor edge. Because walls are very rigid and much taller, you get very little movement over the full wall panel. So what you want to do when you're building with load-bearing brick is locate the masonry support away from that floor slab edge and away from that junction to ensure that it's not affected by any movement. And this detail sort of explores that in a little more depth. So the masonry support angles were set to pick up all the heads of the windows and the door openings in the facade. And so we have a masonry support angle on every floor, and that picks up the brickwork. Now, we didn't need to do that. The brickwork could have been supported every 2 floors. But we felt rather than using separate lintels, this was a better, more efficient approach. It also made it really easy on site for the masonry support subcontractor to come in and put those in. All they had to do was follow the line of the pre-cut windows all the way around. So there was no kind of measuring out as such. You just had to locate it directly above the opening. And like I say, the brick on the outside is all kind of solid brick, not brick slip. That's just a shot on site. Interestingly, the timber that's shown there within the openings, the horizontal pieces of timber, the manufacturer left those in during the manufacture so that once it came to site, we didn't need any additional temporary protection on the outside. So when you're working inside the CLT building, during the process of it being constructed, we didn't need to put any barriers across the openings. So there's a whole cost saving there against the temporary works kind of part of the build. And then those horizontal elements were just cut out later on once the windows came to site. Just another detail here showing the roof level parapet. So at Dalston, what we did was we continued the walls kind of up and past the floor edge, and they created our kind of 1.4 meter high parapets. We had to strengthen those with a small piece of CLT in the bottom right corner. That's just because there was an eccentric load on that parapet edge, but it was just preferable to do that rather than using a glass balustrade or a metal balustrade. Balconies, so at Dalston all the balconies are prefabricated off-site and then bolted onto the scheme or onto the CLT during construction. So at the design stage we worked with Binderholz and BK Structures to develop the bracket connection for each of the balconies across the entire scheme. We have about, I think, 7 different balcony connector types, and we had to ensure and coordinate the location of all those prior to CLT manufacture. So all the holes for those balcony connectors were pre-cut in the factory in Austria. So that allowed the contractor to put the brackets in during the CLT build, and then the balcony supplier to crane those balconies into position and bolt them on. So again, it was all about trying to use prefabricated components where we could to increase the speed of the build. So that's it under construction. And just to give you a kind of sense of scale and contrast to the Murray Grove scheme, just that one element of Dalston is equivalent to Murray Grove, so it's a much larger scheme than the one we previously completed. So overall, we were able to provide more homes because of the lightweight nature of the timber. We actually managed to provide capacity for 35 additional homes, 20 of which were built during this build, and 15 of which the client is hoping to get consent for at some stage in the future. But the structural design allows for an additional story to be put on top. So that this was the key driver to making this site viable, and this is one of the reasons why, particularly in an urban context like London, where you have lots of constraints, that a lightweight solution, particularly where sites are quite constrained, makes a lot more sense versus a traditional build. And so, yeah, the CLT was fundamental to the success of this project. Another kind of comparison, so The timber for the frame was delivered in exactly 111 lorry loads from Austria. What's great about CLT is you can design it all in 3D, you can test that it goes together and it's coordinated, and then you can kind of work out the logistics of that and figure out how many loads you're going to need to be delivered to site. So this gave the contractor real confidence that they knew when the timber was going to arrive. It gave them confidence that their program would be accurate. It wasn't affected by the weather. There's no curing period for CLT, unlike concrete. There's no big heavy mixes on the road. It's a much kind of easier, quieter way of doing things. And this comparison is just a frame comparison. What this doesn't take into account is that if you're building with concrete frame, you have to come back and then put something else in between the concrete columns to complete the structure. With CLT, you're getting the walls and the structure. With concrete, you get the frame, and then you end up putting a steel structure or a masonry structure in between those columns. So all that has a time attached to it. So our engineers inform us that we used about 2,500 trees to create the CLT for this building, and that there were 4,500 meters cube worth of timber. So the sequestered timber within that CLT frame is equivalent to about 3,500 tons, and there was less than 1,000 tons used to produce it. So it's a carbon negative structure. And I mean, that just kind of sums up why, one of the kind of fundamental reasons we're trying to use this product. And that's just a few more images of it completed. This space on the left, interestingly, is the office space. So that's designed to have all the CLT soffits exposed. So again, one of the advantages of the material is it's a beautiful material. And if you can design it from the outset with that in mind, you can create lovely areas where you can keep it exposed. So in the end, we met our sustainability targets quite comfortably. We overperformed on air tightness without even trying. That's by virtue of the fact that timber is so precisely engineered. It comes together so tightly that you get a very good inherent air tightness. So that was far above what we were expecting. And also when we had the building tested, acoustically tested, we found that we'd gone 8 decibels above the requirement, so a lot more than we'd actually anticipated. And again, I think this is because there's not enough evidence of sound testing of CLT buildings at the moment. That is improving, but I think people underestimate how good it can be at creating really good acoustic barriers, which is why companies like Moxie are using it for hotels. And there's the completed building. So just a final kind of piece here. So Waugh Thistleton were commissioned by the American Softwood Lumber Council, I think, to produce a study based on 100 UK CLT buildings that have been completed. The reason for this was that in America, North America, particularly in Canada, they have a huge timber resource that they're not really using at the moment. America is obviously known for using its kind of stick frame, lightweight timber frame kind of construction approach. And the softwood board there feel as though there's a whole new market that they can get into using CLT. So at the moment, the UK is kind of leading the charge for the use of cross-laminated timber and engineered timber products. And we were asked to put this book together that would kind of collate all those example projects in a way that allowed analysis and review, and would also kind of identify strengths and benefits of the product. So we asked lots of different architects to put forward their buildings and contribute to our kind of survey. We had questionnaires by which we took answers and then drew analysis from. We also talked to all the key European CLT manufacturers to understand exactly some of the kind of drivers behind the way in which they manufacture, how much can they produce, how much goes on the back of a lorry, how much does that cost, those sorts of factors, so that we could collate this all into one book that would be a really useful resource. So yeah, we drew 100 case studies from across the UK, lots of different types of buildings. Interestingly, a lot of those case studies were within central London itself. I think that kind of reflects the fact that CLT is particularly good in urban environments where you have constraints on the site, or where you have constraints below the site that might dictate a timber approach. Also in London, this kind of expediency to build and develop things quickly is really important for clients. They want to be able to turn around their buildings very quickly, so CLT can help to deliver a much quicker build program and get buildings on site a lot faster. So I think that's why we see a lot of buildings in London. Plus it tends to be, London is a leader for a lot of things, and a lot of the kind of architectural talent is located there. So there's more of a willingness to innovate, I think. So yeah, it's quite a lengthy book which you can download for free. It includes lots of case studies which really varied in their kind of sectors and typology. So for example, this is a school project completed by Sarah Wigglesworth Architects. Schools particularly have been using CLT for quite a while. The key reason that people are using CLT for schools is that the academic year tends to start in September and finishes in June. So if you need a new building for your new academic year, then you want the certainty that it's going to be completed in time. So we see CLT used a lot in schools because it gives that program certainty. We also see it used a lot because the timber can be used in an exposed finish. And I believe it's been proven in studies that, particularly in school environments where you have exposed natural finishes within the building, it's been shown that students' heart rates drop and it's a better place to work and a better place to be in. So yeah, that's certainly one of the drivers behind why schools are using CLT. This scheme here was a scheme by Doug and Morris for a swimming pool. It was also actually at a school, but one of the reasons they used CLT on this scheme was that the geometry for the roof was particularly complex. Now the great advantage of CLT is that when you manufacture it, it can be cut to really complex geometries and really tight tolerances. So if you want to achieve a form like this, which is almost like origami, then the certainty of bringing those panels together and knowing that they join perfectly is massively beneficial. So that was one of the drivers for CLT here. We've seen it used in private houses as well. So several of the case studies were private houses where you've got a bit more scope for experimentation with the product. Again, this kind of combines the complex geometries with the exposed finishes. And they were drivers in this instance for CLT use here. And then another scheme there, which was a Sterling Prize nominated scheme last year. Again, there's quite a lot of complexity, but the CLT has been used to create different forms and is used in an exposed way to create the internal finishes as well. So as clients, I think as more people begin to understand what CLT can do and how you can use it, you realize that by building in CLT, you can forego a lot of other kind of secondary products to create what you're wanting to build. And then the book, this is just an example slide from the book, but the book takes all those 100 case studies and draws down conclusions and analysis about each of those case studies in order to inform readers about the reasons behind why they're using CLT. So if you do pick up the book, there's lots of kind of statistics and things in there. And as a result of this kind of, both our own work over the last 10 years and this kind of case study exercise, I think we're able to say with confidence some of the things that CLT brings as a benefit. So speed is always one of the key reasons CLT is used. Because you can prefabricate all the panels off-site, it allows you to shorten the construction program once you're on site. Most CLT buildings will always require some degree of concrete in the ground. So whether you're digging a hole or whether you're placing foundations in there, there is a degree of concrete that's going to be required. But after you get kind of 150 millimeters above the ground level, it can all be CLT. And once it gets to site, you effectively, on big schemes like Dalston, you're building roughly a kind of floor every week and a half. So it's very, very fast. And you need a limited team to create this as well. You need maybe 4 or 5 people on site for a large scheme. So it's just a nice way of doing things, very quick, very efficient. Murray Grove, I think, was constructed in 48 weeks. The original build program, based on a concrete scheme, was 72 weeks. So we shortened the program using CLT by over a third on Murray Grove. At Dalston Lane, we estimate that the program was shortened by about 20%. We also know that the timber was constructed in exactly 374 days, which worked out to about one floor per core every week and a half, I think. So really, really fast. And of course, that timber is giving you the structure and the infill. So I think a concrete frame is kind of as quick in terms of its structure to get it constructed, but then you don't have any requirement to come back and infill that. Precision, so I mentioned precision a little bit. All the openings on CLT buildings can be prefabricated in the factory. As designers, what's exciting is you can develop something in CAD, and then that CAD goes to the factory, and then it's all CNC cut to high levels of tolerance, and what you design is what gets built. So a lot of responsibility, but it gives the designer a lot of control over what they're delivering. And in terms of precision, it really is that precise. You see these panels come to site, and they all just slot into place. The timber itself has a moisture content of about it's 12% plus or minus 2%. So there isn't a lot of movement in the panels themselves, and that's why you get these very tight tolerances. Very, very precise, allows you to do complex geometries. In contrast to concrete, which is just poured, it's a wet trade. You got to wait for it to dry. You got to put steel work in there. It's loud and nasty. Secondary structure. So again, one of the good benefits of CLT is that there isn't a requirement for another trade to come in and complete the structural design or complete the kind of envelope for the building. You're getting a lot of bang for your buck with the CLT because it's giving you everything straight away. The other advantage of CLT, particularly with regards to the precision, is that as a contractor, you're able to, with confidence, go and procure the other elements of the building. So we know these windows are going to be cut to within 2 millimeter tolerances. That means the contractor can go and order all the windows in advance. They don't need to come to site with a measure and check them before they order them. So it really aids procurement. That accuracy and that precision also drives better fabric performance. So as we saw with Dalston, we had we bettered the air tightness twice over without particularly introducing any specific measures to do so. By virtue of bringing together components that are highly and tightly manufactured, we're not having to rely on third parties to complete the design. So what tends to happen a lot in the UK, probably the world over, is that on a Friday afternoon, if the builder wants to go to the pub, they're not really that interested in doing a fantastic job. They'll just leave it. With CLT, there's no kind of chance to get it wrong. It does just have to fit in like a jigsaw. And so that's what drives really good fabric performance. One of the other key advantages of CLT is that it has a very good resistance to cold. So we all know timber is a warm material. Unlike steel, which transfers cold and heat very quickly, timber is a much more stable sort of product. So in terms of the kind of, if steel gets very hot and very cold very quickly, then timber kind of levels just gently like that. So that natural characteristic of the timber improves the thermal profile for the building and the thermal performance of the building. That helps us to reduce insulation. So there's a cost saving on the insulation there. It also helps us to reduce the need for other secondary products to improve the building fabric. So that's, again, another one of the large advantages, both in terms of air tightness and thermal performance. And follow-on trades. So if you are an electrician or a plumber, fixing to CLT is very, very easy. It's just like any wood product. You can get a drill and screw to it. It's very quiet. It's very quick. There's no nasty kind of concrete dust. It's not loud to fix to. And it's just a very clean, dry environment in which to work. So we always hear from subcontractors, they're really surprised how easy it is to work with. But yeah, it is a really nice environment to be in. Also with CLT, we've got less requirement for trades on site. So in terms of site logistics, you don't need as many tradesmen on there. As we've seen, you don't necessarily need lots of temporary protection. You can work inside at the same time as working outside. So this slide on the right from Dalston Lane shows that the scaffold for the brickwork is getting constructed. Meanwhile, on the inside, they're doing the first fix, electrics and the plumbing. So again, that's helping to speed program by reducing trades on site. And inevitably, it's a lot safer. If you're putting together a jigsaw, it's pretty safe. If you're having to create that jigsaw out of wet materials and combine lots of small elements together, it's a lot more difficult and there's a lot more risk involved. So yeah, CLT sites, both on-site and in factory environment, are just a lot safer, a lot quieter, a lot safer, a lot easier to work with. And these are just some statistics, I think, from the Dalston Lane project where we acknowledged there was a 20% saving on program. The timber was so much lighter that it contributed to a more dense, taller building. We reduced deliveries by nearly 80% by using CLT, and the people on site at any given time was much reduced for the CLT frame. Like I say, I think Dalston was built using a team of 4 or 5 men over 1 year. Just a final note, so I think as a practice, obviously we're interested in developing schemes from concept to completion, but our position in the marketplace and our expertise with the material has now led to us to set up a kind of specific consultancy firm. So we are hoping to kind of work more closely in new markets with people that haven't used the material before to kind of pass on our knowledge and to work on projects to consider how they might be delivered using timber. Over the last few years, we've taken a lot of traditionally designed schemes and developed them and delivered them using timber. And I think our WTX brand is what we want to kind of take forward internationally, so that we can try and see CLT in the marketplace a lot more often. And this construction revolution that we're trying to bring about in the UK, we really want to kind of push that across the world and internationally. So yeah, if you are interested in working with us or asking us to look at one of your projects, then do get in touch with us. And then yeah, final note, if you do want to have a look at the CLT book, the CLT book we produced, we've made available for you to download for free. It's open for anybody that wants it. All you have to do is log on to that website at the top, give some basic details, and you can download the book. And there's lots of good stuff in there. Like I say, it talks about all the benefits, gives you lots of case studies, from multi-story to private houses to schools, lots of different things. So if you're interested in learning more about CLT and interested in learning more about how you can apply it to your project, then have a look or give me a shout afterwards. Thank you.
Thank you, Kieran. Ar auditorija būtų klausimų? Questions?
Thank you very much for the presentation. More or less practical question. How do you deal with the moisture on a building site during construction? And the other question, how do you deal with the fire safety on the site during the construction?
2 good questions. So timber is breathable, it does get wet, it will take on water if you leave it on site. Both we as a practice and the subcontractors that develop the timber frame have a series of QA processes which involve simple things like sweeping the water off after it rains. We also ensure that before, say, the roof is installed, that the subcontractor will do moisture readings of all the timber, so that as long as it's below 20%, we know we're okay to add those materials on. The other thing that we're increasingly trying to do is use breathable products. It's not always easy to use breathable building materials because of certain constraints. I think insulation has been a particularly difficult one. I think going forward, what we're seeing in our own projects and other projects is that timber buildings are the idea that you use a sustainable, breathable material for the structure is also translating to those external materials. So, for example, the Vitso project, we used a wood fibre Gutex insulation, and the membranes we've got have a permeability that allows that building to kind of vary in its moisture. So I think it's just about understanding the product and using our experience to design for that. We know timber is going to get wet, but as long as it's within certain parameters and it's allowed to wick that moisture out, then that's kind of how we deal with it. In terms of fire resistance, so during the build, there's in the UK there's something called the 16 Steps to Fire Safety, which was developed by the Structural Timber Association, and that sets out all the ways in which you have to safeguard a traditionally timber frame site. In the UK, well, timber frame stick system is a lot more vulnerable to fire during construction because it's a different sort of product, and there's usually, for example, with a stick frame, you're infilling it with other products, and until it's finished and completely sealed, you have no fire resistance. With CLT, we always have that inherent fire resistance from the start. So yeah, it needs to be taken into consideration, but it's a much lower risk product than kind of stick system timber frame. Again, that 16 Steps to Fire Safety, if you're interested, can be found online and downloaded for free as well. So come and ask me if you want the link for that.
Dar klausimų?
Yes, I represent the Lithuanian Association of Civil Engineers. Yes, I heard such a terminology, timber engineer. Could you explain why who is timber engineer? Should I be a chartered engineer? Is it enough to be a bachelor or master or structural engineers institution member? Who is timber engineer? That's, could you explain?
So we say timber engineer, but they are structural engineers that have a specialism in timber, so an interest. So they are normal chartered engineers that have just gone on to specialize in a particular field, I suppose, in the same way you might specialize in civils or specialize in bridges or something like that. So we, as a practice, we work with people, we work with engineers that are leaders in the field of developing and using timber products. But yeah, they can also do normal traditional stuff as well. It's just that they love timber like we do. So yeah, no special provision, just a love and an interest for it. That's kind of all it is, really. Does that answer your question?
What kind of legislation, what kind of documents or attestation, what I have to have?
I'll be honest, I'm not sure. I'm not an engineer myself. In the UK, you would just have to be a chartered engineer. I don't think there's anything above and beyond that. But I'm not sure. I can put you in touch with somebody that would know the answer to that if you want.
Maybe more questions? Oh, okay.
Thank you for a good presentation. One of the challenges in multi-story wood buildings is the shrinkage of the wood because of drying and loads, especially parallel to the fibers. In the project you presented, how much it was in numbers, in millimeters per floor, and totally in the whole building, in a top floor after, let's say, 1 year after building?
So the initial appraisal, if I can remember correctly, the 10-story element, the tallest element of the scheme, the original profile, creep profile on that was 60 millimeters. So that's why we decided to introduce the grout pockets into the floor edge. So we reduced that 60 millimeters down to about 20 millimeters over the movement of the building. At each floor edge, I think they've allowed for about 2 millimeters, 3 millimeters maximum. So it's, in terms of detailing for the rest of the building, all our brickwork and all the masonry supports that carry that brickwork have traditional 10 millimeter movement joints. So even though we're using timber which does move a little bit more, there's no other specific provision in terms of movement other than those grout pockets at the floor edges. So yeah, it's just one of those design considerations we was acknowledged early on and then was detailed by the engineer.
Some more questions? Okay, I have a question myself. We see that in the Great Britain there are really probably, if not the first biggest amount of CLT projects as in a country in the world, but among one of the biggest, or one of the largest amounts. So what exactly was the break-even point to start on such large-scale buildings, and what arguments helped to convince developers, owners, investors to go this, in particular view, risky way? What was this break-even point, and who helped to break that ice?
Very good question. I don't think we're actually there yet, to be honest, for this. I think we're getting there. So when we completed Murray Grove in 2008, nobody really knew what CLT was. There'd not really been a multi-story building. And that certainly put CLT on the map. I think each developer, as we've worked with them, has always been skeptical about the use of CLT. And typically the way in which buildings are procured in the UK, you look at the bottom line cost. Concrete frame is cheaper, and that's what the construction industry knows. It's an old industry with people that have been in it for years and years and years, and they stick with what they know typically. So the kind of key reasons we've seen an uplift in CLT, particularly in London, is partially because of this acknowledgement that CLT gets you a completed building more quickly. It allows you to deal with really constrained sites. So because you can crane panels in and over buildings and into certain places very accurately, if you have a tight site with no logistical room for kind of cement mixers and storage and things like that, then using a kind of prefabricated system like CLT allows you to do kind of just-in-time deliveries, as we call it. So that lorry can come to site, crane the timber straight into place, and then it's fixed down. So yeah, particularly in London, I think where we've had constrained sites, that's where we're seeing a lot of CLT. Also, a bit like Dalston, where you have other constraints that relate to the weight of the building and the mass, we've seen other kind of multi-story schemes go up where CLT has got over that problem. And then increasingly, I think architects are keen to use it. My bosses particularly, they've really believed in this as a material for a long time. Firstly, on an environmental point of view, but all the other benefits I've just run through there are very, very true. It does give you so many advantages over a traditional frame. And that cost price is coming down now because there's more competitors in the market. So when we did Murray Grove, there was literally 2 or 3 CLT providers on a large enough scale to do that scheme. Now we have many more providers across Europe. And even today, I'm hearing that we've got a couple of CLT providers in Latvia coming to the market, for example. So it's growing, and that means cost is coming down. And once cost comes down, that is fundamental to the UK construction industry and the people that commission these buildings. For us, it's about making the argument that all those benefits give you a more cost-effective building. But you have to kind of go through the process once to really understand it. So a lot of clients at the end of a project will go, now I get it, but they don't always believe us.
And one sensitive question. Andrew Waugh told that every single new building should be from wood. Would be there enough material and sustainably forested material? What are figures?
So certainly with European forests, yes, because they're well managed and it's an industry. So if you go to Austria, I think timber is the second biggest economic contributor to GDP. It's a sustainable economic system. Now that's not the case in all countries. At the moment, the UK doesn't really have the right timber or the industry for making its own CLT at the moment. And actually, my dad was a sawmiller, as it happens. He used to cut timber himself, so I kind of know that firsthand. there's certainly enough capacity, and I think the hope would be that if ever we get to the point where we might exhaust that capacity, which I don't think will happen, but if we continue to build more buildings, the industry that supports that will grow up behind it, and forest management will become a bigger thing. But just as a contrast in terms of how much timber is available, the timber used in the Dalston scheme was calculated to have regrown within 3 hours. So the equivalent volume of timber grew 3 hours later within the forests in Austria from which it was sourced. So that capacity at the moment exists. But yeah, we obviously have to think carefully, if it really takes off, how that's managed.